Okay, I'll get started with today's class. I wanted to begin with just a sort of big picture, big perspective of what we're doing right now, what we're covering right now. We're covering light. So on this slide, we started over here in the top left. We discovered from Maxwell's theory of electromagnetism that light is an electromagnetic wave. That launched us to over here on the top right and studying properties of light. Most importantly, we talked about reflection, and we talked about refraction, and we talked about mirrors, and we talked about lenses. Then we moved down here to the bottom right. That's what we're doing now. We're talking about wave phenomena. In last class, it was interference. This class is diffraction. And then finally, on Thursday's class, we're going to end up over here on the bottom left, complete the circle, and we're going to talk about the speed of light and what it means, the strange things that it means for the nature of space and time. And so this will be a kind of plan, a complete story of light, if you like, to walk around this path. Okay. Enough of that. Let's get on with actual material for today's class. And we're going to talk about diffraction. And if you want to explain diffraction to your, I don't know, to your mom or your dad, diffraction is seeing around corners. The diffraction is the bending of light around corners. The diffraction is the bending of waves around corners. And we're going to explore diffraction. So we're actually going to start by introducing the phenomena of diffraction, the nature of diffraction, some illustrations of diffraction. So that's topic number one here. And then we're going to get much more specific. And when we get much more specific, we'll be able to write down equations describing diffraction, make diagrams describing diffraction, look at examples of diffraction. We're going to look at one specific case, which is called single slit diffraction. And we're going to explore that in some detail. And then we're going to look at a second specific case. It's called multislit diffraction, and we're going to explore that, examine that in some detail. And so this is the path for today's class if this mission is successful. Okay, so let's begin with, we better figure out what diffraction is. We better understand what diffraction is. So that's the first step. Well, on this slide, I'm comparing a property of particles with a property of waves. So on the left-hand side of this slide is a situation involving particles, and on the right-hand side is a situation involving waves. In both cases, the particle and wave situations, I've got on the left a stream of particles that is traveling from the left to the right. And on the right-hand side, I've got a stream of waves that's traveling from the left to the right. And so I pictured the stream of particles. Oh, I knew that was going to happen. Pictured the stream of particles here, the arrows indicating they're going left to right, and the wave fronts here, the arrows indicating, again, they're going left to right. And the particles strike a barrier. And the waves strike a barrier, and that in the barrier there are thin slits, and in the barrier for the waves there are thin slits. And on the right-hand side of the thin slits, on the right-hand side of the barriers, we see a thin stream of particles emerge on the left-hand side, where it was particles impinging on the slits. We see circular wavelets of waves emerging on the right-hand side, where the waves are impinging the barrier. And you see very different effects. You see on the left with the particles, which are localized in objects in space, you see just a stream of single thin stream of particles pass through each slit. On the right-hand side, where we're working with waves which are non-localized in space, we see these circular wavelets, spherical wavelets emerging from the slits. On the left-hand side with the particles, there's no such thing as interference of the particles. On the right-hand side with the waves, there is going to be interference with the waves. And this bending of the waves as they pass through the slit, that they emerge in all directions, which is quite unlike the particles when they pass through the slit, is what we call diffraction. So in short, I wrote down here, waves can bend around obstacles. The waves are bending around these slits. Particles don't bend around obstacles. The particles are not bending around these slits. And so this is a big difference between particles and waves. This is the wave property of diffraction. So that's what I've introduced here. I got now just a few pictures of diffraction of waves. Now, light is a wave, sound is a wave, the ocean, rivers have waves. So you can have diffraction with, water, sound, and light waves. And so I'm going to just show you a few pictures, a couple of them with water waves and one with light waves. So look at this picture here. Was I just going to show you a nice picture of the beach and the ocean? No, I'm not just showing you a nice picture of the beach and the ocean. I'm showing you this fantastic, I love this picture, fantastic picture of diffraction. Look, we've got an array or an arrangement of, in this picture, of thin slits. Here's a barrier, if I can draw it. Here's another barrier. And over here on the far left, there's also a barrier. And over here, again, on the far right, there's another barrier. So we've got an arrangement of slits, an arrangement of barriers, and ocean waves are streaming towards, they're approaching these barriers. And each of these slits is a source of these circular wavelets of water waves bending around the barrier. So you can see the waves emerging from this barrier here as they kind of emerge like so. I didn't draw it very well there, sorry. And you can see them bending around this slit. They emerge like so. And so this is an example of diffraction. It was a beautiful picture until I started drawing all over it and really messed it up. But it is an example of diffraction of ocean waves, water waves. Here's a second one. So again, this is water waves. So a train or a stream of water waves are approaching this barrier. So there's a barrier here, you can see it. And the water waves are approaching this barrier from the top right. So maybe there's a wavefront here, a wavefront here, a wavefront here. And then they strike the barrier and these circular wavelets emerge from the barrier. And again, that's the water waves bending around the slit, bending around the barrier. And that is, again, diffraction. That's a diffraction pattern. And then finally, here's an example of light waves and diffraction pattern. So what you're seeing in this picture is actually moonlight from the moon, and it's being diffracted by not actually slits, but water droplets in the atmosphere. And all those droplets, the light is bending around those droplets, and you get a characteristic diffraction pattern, like spherical wavelets emerging or circular wavelets emerging, and you get this diffraction pattern. And it's a diffraction pattern of circles of different colors. And so this is actually a moonlight example of a diffraction pattern. Okay, well, in those three pictures, you actually saw two types of diffraction. One over here on the left, one over here on the right. So in one case, we had the diffraction of waves passing through a thin slit. So here you could imagine this as the thin slit. In black is the barrier, and in white is the slit. And you get this characteristic pattern over here on the light, diffraction pattern of bright and dark fringes emerging from the barrier. And this is given a particular name. It's called Fraunhofer diffraction. It's single slit diffraction. And it happens when light or other waves impinge on a narrow slit. Over here on the right-hand side, this is a pattern. This is another diffraction pattern. It's a circular diffraction pattern of bright and dark fringes. And this occurs when light rays strikes a dish-shaped barrier. So imagine this is the disk here, and light passing around this disk. And this type of diffraction, that's called Fresnel, single disk diffraction. And you get that, again, when light strikes or impinges on a opaque circular disk. There's a question in the chat, I just seen it, from Sarah. Is this similar to why you see a full circle of a rainbow from an airplane? When you see a rainbow, whether you see it actually from the ground or whether you see it from an airplane, you're seeing a phenomena that involves actually reflection and refraction, and that disperses the colors of light. So actually, the moonlight example and the diffraction pattern of the moonlight is quite different in its explanation, quite different in its nature from a rainbow from a plane or a rainbow from the ground, which is simply reflection and refraction. So this is actually a different phenomenon. And one reason you might think it's a different phenomenon, a different effect, is you see here with a single color of light, these patterns were made with red light, you get all these rings or all these lines or fringes of interference of the red light, rather than just a simple rainbow. But that was a good question. Okay. At the heart of understanding diffraction patterns is also interference, the interference we talked about in last class. So I'm just going to go through two slides from the last class just to remind you. We talked about constructive interference in the last class. And that's when two waves collide with one another. Two waves overlap one another. And those waves their crests are occurring at the same time, same place. Their troughs are occurring at the same time and same place. That's shown for wave 1 and wave 2 here. Their crests and troughs are at the same location in time and space. And that causes constructive interference. You get a larger amplitude wave. And then we also talked about destructive interference. And in destructive interference, again, it's the collision between two waves, or the overlap of two waves. But this time, when one wave is a crest, the other is a trough, and vice versa. When the other is a crest, the first wave is a trough. So you see that here for these two waves, wave 1 and wave 2. And in this case, you get destructive interference. The wave cancels out or partially cancels out. And so in the last class, when we talked about, the pattern in water droplets or soap bubbles, interference, constructive, destructive interference was the key. In today's class, when we talk about the single slit diffraction pattern, and we talk about the multi-slit diffraction pattern, actually interference is going to be the key again. And we're going to go on in a moment and explain the single slit diffraction pattern by thinking about the destructive interference that's going on. And when we get to the multi-slit experiment, we're going to think about the constructive interference that's going on. So both of these are going to be useful. So this is a slide that has a lot of information on it. There's a lot of content to it. So, the last two slides, I ran through them. I sprinted through them. And this, not that I could sprint, but I moved through them quickly. This slide, we're going to spend a bit more time on. There's a lot of information on this slide. And this slide is going to lead us to the equation, the formula for the location of destructive interference, or the location of dark fringes when light or other waves pass through a single slit. The direction, the angle of the destructive interference, or the direction angle of the dark fringes for a single slit diffraction pattern. So actually, let's start with the picture over here on the right. So in this picture, we've got, imagine here, we've got it's a stream of light waves or other waves heading towards this slit, this barrier with a slit in it. So downstairs here at the bottom is the slit. Upstairs here at the top is the slit. This region here is the slit itself. The way to understand the diffraction pattern is to imagine that each point in the location of the slit, so between the barrier at the bottom here and the barrier at the top here, each point is a source of these little spherical wavelets, or these little circular wavelets that are emerging on the right-hand side of the slit. And I'm not drawing all the points, but here's one of them. Here's another. I'm going to clean up this diagram, redraw that. Here's one of them. Here's another one of them. And here's another one of them. And here's a fourth one of them. I'm just drawing 4, but you could imagine there's a whole collection of these little points between the slits, and they're all sources of the little circular wavelets, or the little spherical wavelets. This bullet here says, imagine the extra distance that is traveled by wave number 1 compared to wave number 3. So we're talking about, here's wave number 1, wavelet number 1, here's wavelet number 3 as they travel to the eye. The extra distance traveled by wave number 1 compared to wave number 3 is this distance here. This is the extra distance. And that distance, with a little bit of trigonometry, and let me not go through all the trigonometry, but with a little bit of trigonometry, if you're observing the light in some direction theta, so that's theta here, and you're observing the light that's coming from a slit of width A here, then this extra distance, which is the lower side here of this right angle triangle, that extra distance depends on the slit width, depends on the angle you're observing at. It's a/2 times sine theta. So that's the extra distance. And that's just a little bit of trigonometry to figure that out. So waves 3 and 1 travel towards the eye, and wave 1 has traveled a little extra path compared to wave 3. And that path is 1/2 a sine theta. The same is true about another pair. So think about wave 2 and 4. Wave 2 actually also travels a little extra distance than wave 4 towards your eye. And it's that same extra distance, a of 1/2 of a times sine theta. And in fact, every little wavelet that's emerging from the bottom half of the slit has a partner wavelet on the top half of the slit that the wavelets from the bottom half of the slit are always traveling that little extra distance, 1/2 a sine theta, compared to their partner wavelet on the top half of the slit. And that's this point here. And this is a big point, so let me circle it twice. It's saying that if you think of the slit as made up of all these little sources of little wavelets, of little light waves emerging from the region of the slit, then for every little source in the bottom half of the slit, there's a source in the top half of the slit. And the source in the bottom half of the slit is traveling a little extra distance compared to the source in the top half of the slit. And that extra distance depends on the size of the slit, not surprisingly, and the angle that you're observing the light at, not surprisingly. And by geometry, trigonometry, that extra distance is 1/2 a sine theta. Now, here's the key point. If that extra distance, 1/2 a sine theta, corresponds to 1/2 a wavelength of the light, or 3/2 a wavelength of the light, or 5/2 a wavelength of the light, what happens then? What happens is that when light waves 1 and 3 arrive at your eye, when 1's a crest, 3 is a trough, and vice versa. So they interfere destructively. When light waves 2 and 4 arrive at your eye, if light wave 2 is a crest, light wave 4 is a trough, and vice versa. And so they interfere destructively. And so this is the condition for destructive interference, for seeing a dark fringe. It's when that extra distance, 1/2 a sine theta, just from a bit of geometry, is either half a wavelength or 3/2 a wavelength or 5/2 a wavelength or 7/2 a wavelength, and so on and so forth. And so that's the conclusion I've drawn down here at the bottom, is that I've found the condition that gives destructive interference. I've found the direction of the dark fringes based on understanding the interference of the wavelets emerging from the single narrow slit. Well, you can make that statement into a little equation, and here's the little equation that corresponds to that statement. And so this is the condition for dark fringes. You get dark fringes at angles theta when a sine theta is m, which is just a whole number, a positive or negative whole number, plus or minus 1, plus or minus 2, plus or minus 3, times the wavelength of the light. And so this is the condition for the dark fringes. And so it relates the width of the slit to the direction of the dark fringe to the wavelength of the light. And it locks together all those things. And this describes our single slit diffraction pattern. You can rewrite that equation in terms of not the angle theta. Let me point out the angle theta up here on this little diagram. You can rewrite the equation not in terms of the angle theta, but in terms of the position y on a screen that's illuminated with the diffraction pattern. And so, again, it's just a bit of geometry. And it's a bit of approximate geometry that works when the angle theta is small. You rewrite that equation like so. Again, this relates the slit width, the wavelength of the light, the distance to the screen, and now the position on the screen rather than the angle to the screen. And so sometimes we will use this equation. Sometimes this is handier. And sometimes we will use the previous equation. Sometimes the previous one is handier. If I can go back to it. Here we are. They're both telling us when you get destructive interference with a single slit, but one in terms of the angle, the direction of the destructive interference, and one in terms of the position of the destructive interference on the screen. And importantly, one of them, this one is exact. And the other one, that's approximate. The first one's exact, works for any angle, theta. The second one that's not exact is approximate, works for small angles, theta. Okay, let me show you a demonstration of this. So I'm going to share a different screen. And what you're seeing here is a diffraction pattern on a screen where the diffraction pattern was made by illuminating a single slit with green light. So if you just step back and think about this, it's quite an amazing thing. I've got a single slit, like a letterbox, and I've illuminated the single slit with green light. And then I get this kind of glorious diffraction pattern with that bright maximum, and then surrounding it a dark fringe on either side, and then other bright maxima, other dark fringes. And our equations, those two equations we just figured out, they tell us the directions to the dark fringes, or they tell us the locations of the dark fringes on the screen for single slit diffraction. Now, what I'm going to do when I play the video is I'm going to start decreasing the size of the slit. And when you decrease the size of the slit, you're going to change the diffraction pattern according to those two formulas. And actually what happens is, as you decrease the size of the slit, the separation between the bright fringes increases. The angles of the bright fringes increase. And so we're going to see that. And so I'm making the slit narrower and narrower, and you're seeing the diffraction pattern kind of expand and expand. The spaces between the dark fringes and the bright fringes are getting larger and larger. Finally, I make the slit so narrow it cuts off the light. I've shut the slit, and then I'm going to open it back up again. And as I open it up, making the slit wider and wider and wider, you're going to see that diffraction pattern. Distance between bright fringes and distance between dark fringes get smaller and smaller and smaller. And so that's an illustration of the relationship between the width of the slit and the distance between the fringes. Okay, let me go back to sharing my slides. And I just want to show you a sketch of that diffraction pattern that we saw in the video. And so over here is the slit, and the slit width is A. Down here is the separation between the slit and the screen, that's L. And theta is that angle, that direction towards the location on the screen. And that equation, sine theta equals m lambda over A, that tells you the location of the dark fringes. So this red line here is meant to brown line is meant to indicate the intensity of the light. So there's a dark fringe here upstairs. There's another dark fringe upstairs here. And then there's corresponding dark fringes downstairs, one here and one here. And this first dark fringe away from the maximum on either side, that's the first order dark fringe. This second dark fringe away from the maximum, that's the second order dark fringe. And we use subscripts 1 and 2 to indicate those orders of the fringes. And so, for example, the first order dark fringe is located at a direction θ1 given by this equation. Tells you how it's related to the wavelength of the light and the size of the slit. It's basically a comparison between the wavelength of the light and the size of the slit. And then the second dark fringe is located according to this equation here, twice the distance, and again, it's related to the wavelength of the light and the size of the slit. So those are the directions. Here's the same sketch. Light impinging on a slit, slit width A, the slit to screen distance L. But now we're using the equation for the positions rather than the directions of the dark fringes. So again, we're talking about the first order dark fringes just here on the screen and just here on the screen, just above, immediately above and below the bright maximum. And then the second order dark fringe upstairs here and downstairs here on the screen. And we're labeling their positions with 1s and 2s to indicate their first order and second order destructive interference, their first order and second order dark fringes. And here's the approximate equations for those locations that are good approximations when the angles are small, that are not so good approximations when the angles are large. Let's look at an example. So in this example, got to get the pen going again here. In this example, this is actually an example of diffraction of electromagnetic waves, but not visible light. It's actually microwaves, like microwaves you have in your microwave at home or in your dorm, right? Microwaves are electromagnetic waves, but the wavelengths are not hundreds of nanometers. Microwaves have wavelengths that are scale of centimeters. And here we're talking about 5 centimeter wavelength microwaves. And in this particular example, we're told that the 5 centimeter wavelength microwaves enter a 36 centimeter wide window and yield a diffraction pattern on a wall 6.5 meters away. So in that first sentence, we're told actually a lot of information. Firstly, we're told we're thinking about a single slit diffraction pattern because we got electromagnetic waves incident on a slit, the window, and the diffraction pattern appearing on a screen. So this is a single slit diffraction pattern, and we're told the wavelength of the microwaves, lambda. We're told the size of the slit, that's this window width, 36 centimeters. I've missed out the centimeters here. And we're told the distance to the screen, 6.5 meters. And so I've sort of pictured all that information down here. It's real helpful to draw the situation. Here's the slit width, 36 centimeters. Here's the wavelength of the electromagnetic waves, 5 centimeters. Here's the screen to slit distance, it would be 650 centimeters. And the question is asking us, at what location does the first order minimum, the first order dark fringe, the first order destructive interference occur? So we're going to try and answer that. And I'm actually going to do it 2 ways, because I gave you 2 formulas. There's one formula, which was the approximate one, which gives you directly the location of the first order dark fringe on the screen. And then there was the second equation, which is not approximate, which gives you the direction to that dark fringe on the screen. And we're going to use both of those. And in that way, by using both of them, we can see how good or bad the approximate one is by comparing it to the true and accurate one. So that's the plan. Okay, so this is my solution to the problem. Both methods are on here. I just reproduced the diagram again downstairs here, so we had it. And then I'm going to calculate first the location of the first dark fringe with the approximate equation. And then I'm going to calculate it second with the accurate equation down here. So let's do that. So firstly, with the approximate equation. Here's the location of the dark fringes, and I filled in that this is the first order dark fringe, so m equals 1. And so if m equals 1, we got this little relationship between all these dimensions in the problem, slit width, screen distance, wavelength, things we know, and the location of the dark fringe, what we don't know, y1. And so I just rearranged this for y1. And y1 equals the wavelength of the light times this distance to the screen divided by the slit width. And I filled them all in. I filled them all in meters here. And I got the location of that, that dark fringe on the screen. And it was at 90 centimeters from the center, or 0.90 meters from the center. And so that was straightforward enough. Second calculation. So I'm going to ultimately calculate the same thing. But I'm going to do it with a formula that is exact. And I'm going to do it by first calculating the angle the direction to the dark fringe, and then, only then, will I calculate the position. So I took the equation involving the direction of the dark fringe, again, plugged in that this is the first order dark fringe, so plugged in m equals 1. I get a sine theta equals lambda. I then rearranged that to find theta. So I took the a and divided both sides by a. I took the inverse sine of the left-hand side and the right-hand side. I get this little equation here, and I plugged in the wavelength 5 centimeters, the slit width, the 36 centimeters, and I get this angle here, 7.393 degrees. Now that's this angle in this triangle. I know the adjacent side of this triangle is the screen distance, so it's 6.5 meters. I want the vertical side of this triangle. It's the distance to the fringe from the center. And so finally then, to calculate the distance to the fringe from the center of the diffraction pattern, I just used the trigonometry of this right angle triangle, that tan of this angle is the opposite over the adjacent, or the opposite is equal to the adjacent times the tan of the angle. And I filled in the distance, the adjacent side, 6.5 meters, and the tan of the angle. And I got 0.91 meters. So you might want to compare the two numbers in that calculation. With the approximate formula, we got 0.90 meters for the maximum. With the accurate formula, we got 0.91 meters. So they're actually really rather close in this situation. And they're really rather close in this situation because the angles are really rather small, 7 or 8 degrees. Okay, I have a quiz, so let me try and publish the quiz. Okay, I think time's up on the quiz. Let me give you the answer to the quiz. The quiz question asks you, in single slit diffraction, supposing you increase the width of the slit, what happens to the diffraction pattern? Do the pattern shrink? Do the minima get closer? Or does the pattern expand? Does the distance between the minima get larger? Well, when you increase the slit width, what happens is the pattern shrinks. The distance between dark fringes gets smaller. The distance between bright fringes gets smaller. So increasing the slit width decreases the pattern. We saw that in the video. In the video, I actually first decreased the slit width and the pattern expanded, and then I opened up the slit width, the case in this quiz, and the pattern shrank. The distance between fringes shrank. Okay. I'm going to skip this. There's a second example of diffraction in here, but I'm going to skip that. You might want to take a look at that example. And I'm going to move on to a second quantitative topic, which is multi-slit diffraction. And I'm going to explain multi-slit diffraction. And in this slide, what you're seeing is in this slide, you're actually seeing another slide. Never thought about that. And that other slide that I'm holding in my hand there, that slide contains a multi-slit diffraction grating. We call it a diffraction grating when you've got multiple slits. And just to make it clear, let me draw all over it, if that makes it clear. So here's a slit. Here's the neighboring slit. Here's the neighboring slit, and so on and so forth. So there must be, 30 slits on this slide, something like that. So that's a multi-slit diffraction grating. So we use this word grating. We say multi-slit diffraction grating, or we just say diffraction grating, implying that it's a multi-slit diffraction arrangement. I even have one. Let me show you this. This is my own personal multi-slit diffraction grating. And I don't know if you can read, it's probably really hard to read that. I got it from Science Stuff Inc. You can see that there. And I'm going to read out, it tells me that I got 1,000 lines, which means 1,000 slits. 1,000 lines or slits per millimeter. So on this diffraction grating, there's an enormous number of slits. So a diffraction grating normally has many more than the 20 slits on this slide, in this picture, in these overheads. It has thousands and thousands of thin lines. Okay. And these diffraction gratings create very interesting patterns of diffraction. And these diffraction gratings allow you actually to measure the wavelength of light with very high precision. And let me see, can't get out of pen mode. Here we are. This slide just shows you an interesting evolution, not the evolution of humans from rabbits or wherever we came from. It's the evolution of the diffraction grating from a single slit. So if you look at this slide, this is a diffraction pattern from a single very narrow slit. It's this guy here. The second little sketch picture is the diffraction pattern from two slits. And you see you get this fine detail here. And we talked about both these cases in today's class and the last class. The third picture, that's 3 slits. Then 4 slits, then 5 slits. And what you're seeing happen as you walk from the broad single slit diffraction pattern towards many slit diffraction patterns is that you get larger and larger regions of dark, destructive interference. Sounds gloomy. And then you get these intense spots, very intense spots of constructive interference. And well, I'm just showing you the walk from 1 slit to 2 slits to 3 slits to 4 slits to 5 slits. You can imagine, just imagine in your head what happens when you go to thousands of slits. There's huge expanses of destructive interference and then tiny specks or dots of constructive interference. And that's a diffraction grating. That's what we mean by a diffraction grating. And again, understanding the pattern of light from the diffraction grating, like understanding the pattern of light from the single slit and also the double slit from the last class, is a matter of understanding constructive and destructive interference. So actually, for the grating, diffraction grating, it's going to be more important for us to understand those tiny regions of bright spots or bright specks. So we're going to focus on the constructive interference. And we're going to focus less actually on the regions between those bright spots where there's destructive interference, where the light rays from the slits are canceling one another out. So we're actually focused less on this case, destructive interference, and more on the constructive interference. And so here's a diagram to try and explain what's going on in the diffraction grating. And unlike the single slit diffraction and the double slit diffraction, two slit diffraction from the last two classes, I'm not going to actually show you how to derive the formula for the diffraction grating, diffraction pattern. I'm just going to give you an idea about how it works and why you get mostly destructive interference and then occasional specks or spots of constructive interference. And this diagram is to show you explain how that happens. So let's look at this diagram. Over here on the left-hand side, I've got light, red light, green light, blue light, approaching a diffraction grating. And on the diffraction grating, you see the obstacle here in brown. You see the little slits, one at the top here, one below that, one below that, one below that, one below that. And in a real diffraction grating, there are thousands of these slits. So light can pass through those slits. And the light that gets through those slits emerges as these little spherical wavelets or little circular wavelets into the space on the right-hand side of the slit. And as that light travels, those wavelets, spherical, circular wavelets travel towards the screen, they interfere with one another. There's destructive, constructive interference. What's interesting about the diffraction grating is you only get occasional spots of fully constructive interference. One of them is here, right in the center. And that one in the center corresponds to, all of the light from all of these slits arriving at that location in the center, arriving at that location in what we call phase with one another. When one's a crest, all the others are crests. When one's a trough, all the others are troughs. There's a first order maximum upstairs here and downstairs here that we label with M +1 and -1. Now, what's happening in those cases? In those cases, light from the different slits is traveling extra distances depending on what slit. And downstairs here, light from the different slits is traveling extra distances from the different slits. But those extra distances are always whole wavelengths. And so the regions that you get the bright spots, the first order maximum, the second order maximum, are really, really, really special regions because it has to be a whole number of wavelengths from all of the thousands of slits that make up the diffraction grating. And so that's a really, really, really rare thing to get whole numbers of wavelengths from every slit in the diffraction grating. And that's why you get a tiny bright spot at one specific location and in between a desert of destructive interference. And so it's quite a different diffraction pattern. Let me show you, I think the next slide is a picture that might make it clearer, or at least it's a nice, enjoyable picture. Yeah. Okay, so this shows a beautiful diffraction pattern, or three beautiful diffraction patterns of a diffraction grating. And what it's showing you is three different colors of light passing through the diffraction grating. So upstairs here, here's blue light, here's green light, here's red light, passing through the same diffraction grating. And for that blue light, Here's in the middle, this is the central maximum. And then the specks or spots on the left and right, those are the first order, second order diffraction maxima. And that's where the path from every slit to those points is whole numbers of wavelengths. So you get constructive interference. And then for the green light, the same thing. So this is the central maximum of the green light, and then to the left and right of it are the first order, second order diffraction maxima. And again, you get in little spots of green light. And for each of those little spots of green light, that's where the path lengths to those first order, second order, whatever order maxima are whole numbers of wavelengths different from the different slits of this diffraction grating. And the same thing for the red light. It's the red light diffraction pattern. Again, lots of little spots. And you notice as you go from blue to green and green to red, what are you doing in terms of wavelength? What are we doing in terms of wavelength? Well, blue light is the shortest wavelength. Red light is the longest wavelength. Green light's somewhere in between. So we're walking from 400 nanometers through to 700 nanometers. And as you increase the wavelength, you're going to increase the distances between these locations of the bright constructive interference. And that's what's going on in this picture. And you could imagine, right? I think you could imagine. I know you can imagine that this would be a good instrument, good device to measure the wavelength of light, because it really gives you just a tiny speck of constructive interference. And that position of that speck of constructive interference is determined by the wavelength of that particular light. So you can measure the wavelength of the light with this diffraction grating. I'm going to show you a couple of demonstrations of diffraction grating patterns. So the picture showed blue, green, and red laser light, but I'm going to show you the diffraction patterns of a couple of lamps. One's called a mercury lamp, and we're going to see the colors of light produced by mercury atoms, and one's a hydrogen, the simplest atom, a hydrogen lamp, and we'll see the colors of light from hydrogen. So let me share a different screen. And let's play this little video. So I think this one is I think first I got the mercury lamp. We'll see in a moment. Yeah, and it's a very short video. It's a very short video that took us a very long time to make. It is the shortest video I did so far this semester, and it's definitely the longest one to make, to actually capture on the camera this diffraction pattern. So if you look there, we're seeing the diffraction pattern of a mercury lamp. You can't see the mercury lamp here. We're not looking directly at the mercury lamp. You would see just, bright light if you looked at you'd be blinded if you looked at the mercury lamp. We're looking at the light from the mercury lamp after being diffracted in a diffraction grating. And you see this beautiful sort of fingerprint corresponding to mercury of his violet. That's the shortest wavelength. You see a green, you see a yellow, you see some red. That's the pattern of light that's characteristic emitted by hot mercury atoms. So we have to thank mercury for that, and a cell phone. Second video. This one's the hydrogen. Now hydrogen, I'm sure you know, hydrogen is the simplest atom. Mercury is a much more complicated atom. Hydrogen has a simpler spectrum of light, and mercury has a more complicated spectrum of light. So you'll see this when I show you the hydrogen. There's just 3 colors that we captured, and one of them barely. there's this violet, and it's so violet, it's barely in our eyes' ability to see it. And then there's this nice blue color, looks like a nice sunny day, and there's also red, and it's hard to capture the red. Here we go. There's a little bit of red. That's right now near the infrared. That's why it's hard to capture. And so that's hydrogen. So I feel I know hydrogen and mercury much better after those little videos. Okay, let me go back to sharing the screen of my slides. And let me give you the equation that describes the locations of those fringes, those now constructive fringes. So that's a difference with the grading compared to the single slit. And so this equation here, I've got to get the pen going, rolling again. This equation here, D is now the slit separation for the diffraction grading. Theta is now the location of the bright fringes. M is the order of the bright fringe, so first order, second order, third order, and so on bright fringe. And then lambda is the wavelength of the light. And so this equation is how we interpret diffraction patterns with a diffraction grading. And so let me just solve a problem involving a diffraction grading. And in this particular diffraction grading, we're told that the grading has 200 lines per centimeter. And we've got to figure out at what angle is the first order maximum for 640 nanometer red light. So a basic question about the diffraction pattern of red light from this diffraction grading. Now again, remember that when we talk, so there's a little bit of terminology here, 2,000 lines per centimeter. With diffraction gratings, they always tell you the lines per centimeter, that there's 2,000 slits per centimeter. If you wanted the separation between individual slits, that would be in centimeters, it'd be 1/2,000. So you have to be a little bit careful about this diffraction grading language. That is typically you're told the number of lines per centimeter, not the slit separation between neighboring slits. Anyway, let's go ahead and solve this problem. I made a sketch here. Here's the diffraction grading on the left, all the little slits. Here's the screen over here on the right. And here's the separation between D, between the slits of the diffraction grading. As I say, it's the inverse of the number of slits per centimeter. And so it'd be 1/2,000 centimeters, or in meters, I worked it out in meters. It is 5 × 10⁻⁶ meters between adjacent slits. And we got to figure out this angle here of the first order maximum for light. I didn't write that on here. Light that is wavelength 640 nanometers. Well, it's not a hard calculation once you've got that equation that describes the diffraction pattern. Here's the equation describing the diffraction pattern. It relates the slit separation of the grating and the wavelength that's illuminating the grating and the order of the diffraction pattern to the direction in which you get the bright fringes. And so I can fill in that we're thinking about the first order maximum. So that's m equals 1. And then I can rearrange for the angle to that maximum. So by simply dividing through by d and taking the inverse sign of the left-hand sides and right-hand sides, I get that the angle, the direction to the first order maximum is the arc sine, inverse sine of this ratio, the wavelength to the slit separation. So I filled in the wavelength, 640 nanometers. I filled in the slit separation, 5 times 10 to the minus 6 meters. Obviously, maybe this is unclear. I have to put them in the same units. So I hid from you the unit conversion there. But if you do the calculation, I got just over 7 degrees, 7.3 degrees. And that's the location of that first maximum. Second example, we do one more example. And this is an example not of a diffraction grating for, say, visible light, but it's a diffraction grating for another type of wave, sound waves. And you can actually make a diffraction grating for sound waves. You could make one, at home in your basement if you wanted to. The way they make a diffraction grating for sound waves is by basically stringing parallel wires near one another, next to one another, adjacent one another, to make a bunch of slits, not for the light, but for the sound. And so in this sound wave diffraction grating, we're told that we've got parallel wires. It's made of parallel wires that are separated by 1.3 centimeters. And so they're actually telling us directly here the slit separation for this sound diffraction grating. And we're going to illuminate this sound diffraction grating with sound. Now, actually, in this problem, we're not illuminating it with sound that you can hear with your ears, but we are illuminating it with sound. Sound is vibrations in the air, and there's a certain range of vibrations in the air that you can hear audibly. If you're young. Oh, clearly I'm old. If you're young, you can hear this huge range of sound frequencies, from very low sounds, 20 hertz, 20 vibrations a second, to very high pitch sounds. That would be 20 kilohertz, 20,000 vibrations a second. So that's audible, young person audible sound. As you get older and older, I can warn you that range creeps inwards, and ultimately, I guess it gets shut off. But when you're young, you got that 20 hertz to 20,000 hertz audible range. So this slit, this diffraction grating, is actually being illuminated by what we call ultrasound. And ultrasound, the word ultra is telling you it's ultrasound. It has a higher wavelength than, it has a higher frequency, higher frequency than audible sound. And its frequency is 37, there's a typo here. This is 37 kilohertz, sorry. I'll fix that. Okay. So the question is asking, this is a long story to make this problem, I know. I've got diffraction grating made of wires. I've illuminated it with ultrasound. How many maxima, how many bright spots am I going to make? So we're going to figure that out. And there's a couple of things I want. I want the slit separation, and I want the wavelength of the sound. That's here. And I didn't directly know the wavelength of the sound, but I got it from this relationship between the wavelength of frequency and the speed of sound waves. Sound waves travel at 340 meters per second. The frequency is 37 kilohertz. Plug that in. And I get that the wavelength is 9 millimeters. So you see here, you tend to get diffraction patterns when you've got a slit separation and a wavelength that's similar dimensions. And so the wavelength and the slit separation here are similar dimensions. Okay, so the question is, how many maxima are there? If I can get back to it. How many maxima are observable? How many maxima can you see with this diffraction grating and this ultrasound? Well, this is how I figure that out. It's actually not hard. So this equation here is our equation for the location of the maxima. But you can turn that equation round to be really an equation for the number of maxima. Rearrange it for m. So I just rearranged it for m. And recognize that the angle of deflection, the angle of the diffraction pattern, this angle theta, that has to be less than 90 degrees. Otherwise, you're no longer behind the diffraction grating. You're in front of the diffraction grating. And so plug in 90 degrees. So if you plug in 90 degrees and sine of 90 degrees is 1, you get this little equation that says that m, the order of the diffraction, has to be less than that ratio of the slit separation to the wavelength of the light. We know both of those. We can fill in the slit separation, fill in the wavelength of the sound, and we get a ratio of 1.4. M has to be less than 1.4. M can actually only be 1. You only get one first order maximum in this case of this ultrasound illuminating this, diffraction grating. Okay, well, let me end there. The class, let me just summarize what we talked about. We talked first of all about just the nature of diffraction. It's a wave property of waves. It occurs for sound waves, water waves, light waves. And then we talked about the two specific examples of slits, single slit diffraction patterns and diffraction grating diffraction patterns or multi-slit diffraction patterns. And we introduced equations to characterize those diffraction patterns. Remember, for the single slit is for the dark maxima. For the diffraction grating, it's for the bright maxima. It was an example, both of those are examples of the bending of waves around obstacles.